Okay, hello everyone. So this week's topic is something called electric potential. So I've divided this into three different videos. The first video we're going to talk about just electric potential energy, and we'll use an analogy that you're familiar with from mechanics, which is gravitational potential energy. They're very similar. So that's the first video. It's just talking about electric potential energy. The second video, we'll talk about something called electric potential, which is very similar but different. We'll talk about why that is. And then in the third video, I'll talk about like how to map potentials. So that's the workflow. And I'll go through some worked examples that will hopefully help you with the challenge this week. Okay, so just as a mass, so remember mechanics with if you have something that has mass, and you put it in a gravitational potential field, we say that that mass has potential energy. So just as a mass can have potential energy in a gravitational field, a charge can have potential energy in an electric field. So let's just talk about like that analogy for a second because I think it helps. So let's say like you have a hill and it has, like a height, and you put a mass at the top of that hill and it rolls down the hill. As it rolls, the kinetic energy increases, and the potential energy, which remember has the symbol U, the potential energy decreases. Okay, as the height, as mass goes from like the highest point to the lowest point, the potential energy decreases. It's very similar in an electric field. So let's say we have a uniform electric field, like a charged plate situation where we have two plates and they're oppositely charged, and you know from the preceding weeks that the field in between those two plates would be uniform. Okay, and it would be pointing from the positive charge to the negative charge. If I put a plus Q charge in that uniform electric field, that charge would accelerate from the positive plate to the negative plate. And as it accelerates, its kinetic energy would increase and its potential energy would decrease. Okay, and so like just like in mechanics, remember we said that the work done by the field is equal to the negative of the change in the potential energy. That is true for gravitational potential energy. It's also true for electric potential energy. Okay, so that's basically what this says. That the work done by the field equals the negative change in the potential energy. Okay. So let's just like talk about equations that we know. So let's say let me sort of like paint a little picture for you. So let's say I have a fixed charge, positive Q, and I know that that fixed charge produces an electric field that looks like this, right? It radiates out everywhere in space from the positive charge, like pointing away from the positive charge. Let's say I put a little test charge, like a positive Q, and I'm going to put T for test charge there. And I want to know like what the force of the electric field is on the test charge, or like another way of saying that is what is the force of big Q on little q. You know from the very first module that you can calculate that using Coulomb's law, right? It's just K times the big Q times the test charge divided by R squared, right? And remember that was the first module. So that was Coulomb's law. Okay. Remember from mechanics, if I integrate that force over a set distance, I can calculate the work, right? So work, remember, this is just like from mechanics. Work is the integral of force over some distance, right? So if I integrate, if I like basically plug the Coulomb's law force into that integral, I'm going to get K, which is just a constant, times big Q times the test charge um, divided by r squared. And then I'm going to integrate that like dr. So I'll integrate like 1 over dr squared. Remember, if I integrate 1 over r squared, it's just 1 over r, right? So what this reduces down to is just k, if I do that integral, times big Q times the test charge divided by r instead of r squared. Okay, that's the integral. Okay, and that equals the potential energy. That's the formula for the potential energy as a function of r. Okay, is this. Okay, so how would I calculate the work? Well, it's the same thing as in mechanics. It's just this formula, right? So work is just going to be equal to the negative of that change in U. Okay, so these are the two sort of like important things to take away from this. Okay, now we're going to do a tutorial in this week that sort of like looks at this relationship more in depth, but let me just walk you through sort of like a preview to that. So let's say that I have this charge. Let me draw it down here just because I need more space. So let's say I have this test charge, okay, like positive test charge. And it's in the field of produced by this positive Q. Okay, and I want to move it, like I want to push it closer to the big charge, positive Q. Okay, so let's say I exert a force with my hand. I mean, this is kind of unrealistic, but let me just write. I push it in some way towards big Q. Okay. What is the work done on that charge? Is it positive or negative by the electric field? So remember, the electric field is pushing it. If I were to draw a free body diagram of this charge, the electric field is pushing the charge in this direction. Okay, like away from the charge because they're both positively charged, right? So the electric field is pushing on the charge. I'm pushing it with my hand, and the electric field, I'm pushing it against the electric field. Okay, so the electric field is pushing it, but I'm displacing it in this direction, okay, because I'm getting it closer to the big positive Q. In that case, the work done by the field is negative. Okay, I hope you can see that, right? Because the electric force is pointing in this direction and the displacement is in this direction. So remember, if those remember from mechanics, if they're pointing, if force and displacement are in opposite directions, then the work done by that force is negative. Okay, so we've got negative work, but if I push that force, if I push that charge closer to the big Q, I'm increasing the potential energy of that charge. Okay, so like the work done by the field is negative, but the potential energy of the electric charge, which we also call U, is increasing. Okay, it would be like if I pushed this charge in this direction, like to use this parallel plate example, right? If I push this charge towards the positive plate, the electric field between the two plates is doing negative work on the charge, but the potential energy of that charge is increasing. Right? It's like you're forcing these two like charges together and thus like increasing the potential energy that that charge has. So that if you let it go, right, it would whip to the other side, right? Because and its kinetic energy would increase and its potential energy would decrease, right? Because the two charges want to get as far away from each other as possible because they're like charges. Okay, so so this like little example that I did here basically like illustrates this relationship, which you should sort of like already be familiar with from mechanics, right? Like if the field is doing negative work on a charge, which it is, if I push it, if I push it towards the charge towards big Q, then the electric field is doing negative work on that charge, then the potential energy increases, right? So it's like a negative, there's a negative relationship. Okay. And that is basically what was meant to be written here. I didn't use the space very well. Okay, so like all of this, that's the example that I just did. Okay, so let's talk sign conventions. So this is meant to be a table. It didn't turn out very well. Let me draw it here. These are meant to be columns. Oh. Okay, so this is like a table to show the two different situations. Okay, so when you have like charges, and the work done by, so like if you're basically forcing two like charges together, then the work done by the field is always negative. Okay, which the short form is just that. Okay, which is the example that I just went over. Okay, in that case, the potential energy is greater than zero, or positive. Okay, and the interaction is what we call repulsive. Like as soon as you let go, as soon as your hand let go of that charge, it would repel the big charge. Okay. Opposite charges, it's exactly opposite. So if you have two charges that are oppositely charged, and you like force them together, the work done by the field is going to be positive, right? Like, I mean, we can draw out that situation. Let's say I had a negative Q and all the vectors or all the electric field, which I draw like that, is pointing here, right? And I put a positive test charge here. The positive, the force on the electric, the force of the field on that charge, so like Fe, is going to be towards the negative Q, right? And then the displacement is also going to be like towards the negative Q because there's an attractive force there. And so the work done by that charge is going to be positive. Okay. But the potential, like as this positive Q gets closer to this negative Q, the potential will decrease. Okay, so in that case, it's like the opposite. So the potential energy will decrease. Okay, so it still honors this like relationship, right? Where the work done by the force is the negative of the change in the potential energy. Okay. So hopefully that's clear. I mean, it's a callback to mechanics. So let's just finish this. So the work done by the field in that case is positive. And so in that case, the potential energy is decreasing, right? So you've got a negative change in potential. And we would say that the interaction is attractive in that case. Okay. So here's an example that I think will help you with at least one of the problems on the challenge. So let's say that we want to know like what work would be like what the work would be required to assemble four charges in the following configuration, like what you see here, right? So we've got like basically a square, and each of these charges like at the edges is separated. They're all positive. I shouldn't make the diagram harder to read. They're all positive charges, and each of the sides of the square is 1 centimeter. Okay, and we want to know like how much work is required to assemble this charge configuration. And just the reading in Collage talks about this when we're talking about like bringing a charge in and placing it. We're always talking about the reference point of infinity. This will be important when we talk about electric potential because electric potential is only relevant if we compare two specific positions in space. And so I think it's important to realize that like when we talk about like bringing a charge in and like what is the potential difference between a charge in this position or what is the potential of a charge in this position, we're comparing it to some very, very, very distant point that is so far away that we can just say it's at infinity. And that allows us to say like it has no basically has no energy. Like there's the point of reference is zero. Okay, so starting each charge from infinity. Okay. Let's go through this. So the strategy that we're going to do is bring each charge in from infinity. Okay, and then we're going to calculate the work needed to do that. Okay, we're going to go through like 4 different steps and then add up all the work at the end. Okay, the potential energy, it basically like superposition also applies. Okay, so you can just like add the work for bringing each charge in to that space and then add them all up together. Okay. So like let's go through step by step. So I'm gonna label these charges just to make it easy. I'll label this one 1, 2, 3, and 4. Okay, so step 1 is I'm gonna bring the like I'll just call it charge 1, Q1 in from infinity. Okay. And I'm gonna just place it like in some space, which I'll call the origin. Okay. And so the work to do that, because there are no charges in the space, so the work to do that is just 0. Okay, because there's nothing repelling it. There's nothing attracting it. It's just like 0. And by the way, because all 4 of these charges are positive, the only like force that we're like going back to our table up here, like we're talking about situation 1, so it's going to be repulsive forces. So like the work done by the field, created by any charges that are there already is going to be implicitly negative, and so the change in potential energy will be positive. Okay, so work to bring the first charge in it requires 0 work because there aren't any charges there already. Okay, so step 2, we're going to bring charge 2 in. So Q2 in from infinity, that's implied, to 1 centimeter away from Q1. Okay, so to calculate the work, remember, like go back to this formula that I defined up here. The work is just equal to the change in potential energy, and so it's just this formula here, right? I just have to multiply the 2 charges and then divide by the distance that separates them. Okay, and then it's multiplied by a constant. So it's very straightforward. And work is a scalar, so I don't have to worry about, it's not a vector. I don't have to worry about like the direction, which is great. So I'm just gonna bring that in. So to calculate it out, so let's call this W2. It's just gonna be K times Q1 times Q2 divided by R. And it's what R? It's the R between like it's this R, right? This is R. This is R1, 2. Okay, so it's the R separating those out. So I would just multiply the charges. So it's 2 times 10 to the negative 6 coulombs times 3 times 10 to the negative 6 coulombs divided by the distance that separates them. So 1 times 10, what is it, to the negative 2 meters. Okay, and if I do that out, you should get 5.4 joules. Okay, so that's step 2. Step 3 is I'm gonna bring in this charge, okay, again from infinity, and it's gonna be repelled by both of these charges that are already there. Okay, so I'm gonna have to like calculate the work done to like oppose the field that is produced by those two existing charges. But again, because it's a scalar, it's super easy to do. It's just superposition. So okay, so step 3 is bring Q3 in. And so the work 3 is just going to be K times Q1 times Q3 divided by the distance between 1 and 3. And then I'm going to add that to K times Q2 times Q3 divided by the distance between charge 2 and 3. Okay, so the distance between 1 and 3 is I'm gonna have to use like the hypotenuse, right? It's not 1 centimeter anymore, so that's the only kind of like I think tricky part. So I can pull K. I mean, I almost don't want to do out all these steps, but it can pull K out of because it's a constant. And then it's just gonna be 2 times 10 to the negative 6 times 4 times 10 to the negative 6 divided by root 2 times 10 to the negative 2 meters. So that's the distance between 1 and 3. And then I'm going to add to that the product of charge 2 and 3. So that's 3 times 10 to the negative 6 times 4 times 10 to the negative 6. And then that's just divided by it's this distance here, right? Like that. And that's just 1. So 1 times 10 to the negative 2 meters. Okay, and that should get you around 16 joules. Okay, I think you guys see where this is going. I mean, it's like it's a little tedious to be honest. So the last step, so for you're gonna bring the last charge in, so bring Q4 in, and it's the exact same step, right? So like you're gonna multiply out like so it's K times Q4 times Q1 divided by the distance between those two charges plus Q4 times Q2 divided by the distance between those two plus Q4 times Q3. Okay. And so you can like sub in all those values. You should get like 36.5 joules. And then the final step is just to add up all the, so like work 1 plus work 2 plus work 3 plus work 4. And that's it, right? So like it's you just add those together. And 36.5 and you get 57.8 joules. Okay, so that's basically the first part of that's sort of like what I wanted to show you in the first video. The next video I'll define something called electric potential, which is not to be confused with potential energy. It's unfortunate that they have such similar names, although they are kind of connected. But yeah, so like I'll talk about that in the next video.